Thank you very much for the invitation. So I want to discuss today the solution to a certain enumerative problem and also give some context for this. So I'll start actually just by stating a theorem. I'll call this theorem A. So the setup is as follows. I'm going to fix a pointed curve, which is going to be assumed to be general in moduli. This is a general curve of genus G with n mark points on it. Okay, and then I'm going to fix the same number of general marked points on a projective space. Okay, and then I'm going to ask, so then the theorem is that the number of degree D maps from my curve to my projective space that satisfy the condition that my points on C map to my points on PR is the following. So I'm just going to write a formula. Okay, so this is an intersection number and a Grassmannian, and okay, so I'll write some symbols. The Schubert class here, Schubert class here, and then I have to decorate by something. Okay, so all right, so this is just some formula for now, and I will not explain the notation right now, but I will explain kind of where the players in this formula come from later in this talk, so that they have some geometric meaning, and I'll explain that. But for now, this is just some formula. Okay, so and maybe I should say, so in order for this to be a sensible question, so I'm asking enumerative questions, I need to impose some sort of numerical condition. So throughout the talk, I'm going to write this in a different color. So I assume here that the number of marked points is equal to this number. Okay, so this is the condition that will under which you would expect that you would have a finite answer to this problem, and in fact, for some transversality, for some reasons which I'll allude to, one actually does get a finite answer to this problem. This condition. Okay. So the setup is I have some general pointed curve, and I'm asking that curve to pass through the maximal number of points in PR, and then I'm asking when that happens, then how many are there? Okay, are there questions about the statement? Okay, so I'll give some context for this problem in a little bit, but let me state a second theorem. So one could imagine a generalization of this problem where instead of conditions that look like point is supposed to map to point under my map F, you could ask for points to map to say subvarieties of higher dimension, right? So for example, you could replace this xi with some linear space of arbitrary dimension. And let me state a second theorem. So so again, I'm going to fix a general curve, and let me now state this theorem in P2. So I'm going to deal just with plane curves. So let me fix not just a bunch of points. So x1 through xn naught will be general points, but I'm also going to fix a collection of general lines, maybe which I'll call I guess L n naught plus 1 up to Ln. So I should use this symbol. General lines. Okay, and then I can ask for the number of now plane curves, so maps from C to P2 with, well, so fpi is supposed to be equal to xi for I less than or equal to n naught. And then for I bigger than n naught, now the condition is that fpi just maps to somewhere on this line of degree D. Is okay, and then this formula I will not state entirely, but I'll just kind of give you a sense of what it looks like. And then I'll put kind of a blob here. So in this formula, this kind of blue symbol here means that so this is some integer which I will not explain. There's some Schubert, this is some coefficient. So I won't explain what this is, but let me just say approximately what it is. So this number is supposed to count. So it's a positive integer, and this is a number of semi-standard Young tableau of shape lambda, avoiding certain patterns. Okay. So I don't assume what you know what this means, and I will not really talk about this in this talk. But I just want to say this to kind of indicate that there is some kind of combinatorial formula here. And okay, so I've only stated this for P2, and in fact, you can, of course, ask this question for any PR, as I did for theorem A, where you require your points to map under this F to just linear spaces of arbitrary dimension. And in fact, there actually is a precise theorem that looks exactly like this, except for the fact that, well, that theorem says that the formula will have some shape like this, where this kind of blue coefficient in some precise way should count SSYTs of shape lambda avoiding certain patterns. The reason I stated this for P2 is that I can actually tell you which SSYTs you're supposed to take for plane curves, and then for in higher dimensional projective spaces, it's a little bit unclear. Okay, but for P2, there is a precise theorem which I'm not stating. Okay. So maybe this is where I wish I had sliding boards. Now you could compare these two formulas, and so this formula is sort of saying you have a Grassmannian and you have a class that looks like it's some class to the G and then times some sum, and that sum is kind of written in terms of the Schubert basis. You could compare that to the formula I wrote for in theorem A, which is the theorem I'm actually going to focus on. So in theorem A, you might complain that this looks a little different in that, like, I had a sum of products instead of like a linear combination of Schubert cycles. And for theorem A, in fact, you can rewrite this sum of products in terms of the Schubert basis. And in that case, you get some coefficient, some blue coefficient here. And in that case, in full generality, I can tell you which SSYTs you're supposed to take. So this is actually a combinatorial story that's been that was mostly understood before this work, but okay, so maybe I just want to say that to mention that there's some combinatorics which I will not discuss. Okay, so are there questions about either of these theorems? Okay, so again, I'm really only going to focus on theorem A today, which is actually quite a bit easier. But I just mentioned theorem B as sort of an open direction to kind of so this is the story is kind of complete in dimension 2. And then in higher dimensions, there's this question of like what this coefficient is combinatorially.
So is it safe to assume that if we go to higher dimensions, then the theorem still is true in higher dimensions?
So it's true in the sense that this number is given by so it's true in the sense that this number will be given by a formula like this. The only thing that's missing is I don't know what coefficient you're supposed to put here, and there's some precise statement that says that this coefficient is supposed to be, it's like bounded above by the number of SSYTs satisfying some conditions, but then the question is like which additional conditions do you need to impose to kind of write down a precise formula. Does that make sense? So this is, you could view this as like the upper bound to it. So this is a complete formula in theorem B in dimension 2, and then in higher dimension this is kind of an upper bound for a formula.
Okay, thank you.
Mm-hmm. Okay, but I'm actually not going to focus on theorem B today. I just want to mention it. So theorem A is what I want to really talk about. So this is actually the simplest situation where I'm counting curves that pass through a bunch of points. Okay, so let me start by actually reformulating theorem A in terms of, or at least the question theorem A in terms of some moduli spaces. So the reformulation. Okay, so the most natural place to state this problem is in terms of the moduli space of maps. So so I'm interested in maps to PR of degree D. Okay, this is the usual moduli space, and for now I'm taking the open moduli space. And out of this space, I have two forgetful morphisms. So on the one hand, I can remember the target. I can remember just the domain of a map to PR. And the other hand, I have n evaluation maps where I just take my n mark points and ask where they get sent to. And so I can map I can take my map and I can remember the data of a pointed curve and n points on PR. And I'm asking about the degree of this map, right? So theorem A asks for the degree of this of tau, kind of assuming the appropriate transversality. Which is to say that, well, there's some numerical condition which I've already written under which you would expect this map to be generically finite, and you're asking not only is this map to be expected to be generically finite, you're asking this map actually to be generically finite and to be in fact generically entall. And so the Brill-Noether theorem tells you that basically maps to PR basically always move in families of the expected dimension, assuming the domain curve is general, which I have. So the Brill-Noether theorem implies that tau is in fact generically entall when the kind of expected relative dimension is 0. And the condition that the expected relative dimension is 0 is the condition that I wrote at the beginning, this condition in blue, which I'm assuming throughout. Okay, so now, so this is kind of a kind of well-formed question. I can ask for the degree of this map. But the problem from the point of view of intersection theory is that, well, these maps, these moduli spaces are not compact, right? So I cannot reduce some sort of intersection theoretic calculation in an immediate way. Okay. And well, there's a kind of natural fix to this, which is, okay, I can pass to the kind of well-studied compactifications of these spaces. So now what I can do is I can put a bar over my MGN PRD, and I can pass the space of stable maps. And if I have a stable map, well, my domain curve is no longer a smooth curve, but it's a stable curve, or it's a pre-stable curve, which can be stabilized. So I have a map to MGN bar. And then I still have n evaluation maps to PR at the end. So that part stays the same. And maybe I'll put a bar over the tau. And so now I have compact moduli spaces, and you could try to ask, for the degree of tau bar. But when I do this, there's now a well-understood problem to this proposal, which is that by adding a bar over MGN PRD, I've introduced, or I almost always introduced components that are too large, right? So the problem here, which is well understood, is that MGN PRD often contains, in fact, even dominating components of dimension too large, so greater than the expected. So by dominating, I mean they actually dominate the target of this map tau bar, and they will actually contribute to what you might think of as the degree of tau bar. Okay. And so as a result, you can't really ask the degree of this morphism anymore, because like it's no longer generically finite. But what you can do is you can ask for the virtual degree, right? So instead of asking for the degree, so the degree would be like, I could take the kind of if I were asking for the degree, I would sort of try to take the push forward of the fundamental class, and then I would get some multiple downstairs of the fundamental class. And of course, this doesn't make sense because I can't push forward. I mean, the fundamental class lives in a dimension that's too large, so I'm just going to get 0. But what I can do is I can add a virtual class here, in which case the class on the left-hand side lives in the expected dimension. And the push toward that virtual class will be a multiple of the fundamental class downstairs, and that multiple is by definition the virtual degree. Okay, so maybe I should put bar here. Okay, so this formula is a definition of the virtual degree of this map tau bar. So you might say that the virtual degree of tau bar is a virtual count of the number of curves of fixed domain that pass through the maximal number of points in projective space. Okay. Now, so this is great. So this is now kind of a well-defined invariant. Because I'm on a compact moduli space, you can realize this is some kind of intersection number. Now the issue now is that the second invariant that I've introduced is not the same as what I was asking for in theorem A. So in general, this virtual degree is not equal to the degree of tau. For the reason that, well, when I pass the space of stable maps, I actually add a bunch of stuff that's going to contribute to the virtual degree, but not to the kind of honest degree of the open morphism. Okay, so let me give a simple example of this. So let me assume in this example that the degree of the curves in projective space is at least the number of mark points. So assume the D is at least n. And what I'm going to do is I'm going to produce, in fact, a positive dimensional family of points in the general fiber of tau bar that lives in the boundary. So it does not live in the general fiber of tau. Okay, so I'll do this by picture. Here's PR. And here's a curve C. So my curve C is fixed in general in moduli, and I'm just going to map it to PR by a constant map. That's point X. And then this is a stable map, so I'm going to attach some rational tails. And the mark points P1 through P2, Pn are going to live on those rational tails. So notice that this curve I've drawn on top it's a singular curve, but it's unstable, right? It has a bunch of rational tails which only have one mark point on them. And if I take the stabilization of this map, of this curve upstairs, I get kind of an honest smooth curve that's general in moduli, right? Because all these rational tails will contract. And what I can do is I can take these rational tails and map them to rational tails in the target that connect to the point X to which C is being contracted. I should put dots here. And so what have I done? So this is a stable map of degree. Well, so I have n rational tails. So if D is at least n, I can certainly make such a stable map because I have kind of D worth of degree to distribute along these rational tails downstairs. And so this is in fact a positive dimensional family of maps that lives inside the general fiber of tau bar, right, which goes from mgn bar, sorry, I guess pn, pr, to mgn bar cross pr Lian, but not in the open part, which is where I actually want to count the maps. Right. So in particular, so this contributes to this virtual degree, but not at the degree of tau. So I can compute the virtual degree, and in fact, I'll say what the virtual degree is. But certainly when D is at least n, and actually you can make this inequality a little bit better. You just do not get the answer that I proposed in theorem A. And when I say contributes, I mean, so this is a positive dimensional family of maps because I can take this X and I can move it around. And so it's not a matter of sort of just counting points at the boundary. I mean, I really have something positive dimensional, and then the virtual class is going to give me some sort of mysterious contribution that, in general, is kind of very hard to extract. Okay, so in fact, I've actually defined two kind of genuinely different invariants of this geometric situation. I have a virtual degree and a degree, and in general, they're not the same. Okay, other questions? Okay, So let me give some history for these problems. To my knowledge, the first calculation of a degree of tau goes, in fact, back to the 19th century. So this is Castelnuovo. And of course, he didn't have this language, but he computed what you might describe as the degree of tau when n is r plus 2. So r is, of course, the dimension of the projective space. So this is n as small as possible. So n and d as small as possible. So what's special about the case n equals r plus 2? Well, whenever you have r plus 2 points in projective space, that's exactly the number of points in projective space for which you have 0 moduli, right? So if you have any map to projective space, and you have kind of r plus 2 mark points on C, so the images of those r plus 2 mark points can be mapped to any other r plus 2 mark points by projective linear transformation, right? So in fact, what you're not really counting maps from C to PR plus 2. Sorry, you're not really counting maps from C to PR satisfying incidence conditions. What you're really doing is you're counting maps from C to PR, but like up to the PGL r plus 1 action, right? So let me write this. So maps from C to PR with r plus 2 incidence conditions. This is really the same thing as maps from C to PR out of mod the PGL r plus 1. And these are what you might call linear series of minimal degree. Right, so in this case, you can just get rid of the points entirely. And in this case, what Castelnuovo found is that the degree of tau is equal to this integral. So it's the integral of some Schubert class to the gth power. And let me just mention, so I'll go back to my formula for theorem A. So notice that when n is equal to r plus 2 in this formula, I have a lambda inside some box of size n minus r minus 2 to the r. Okay, so whatever that means, this n minus r minus 2 is 0. So actually, this second term with the sum just goes away, and what you're left with is sigma 1 to the r to the g. And this is the integral Castelnuovo actually knew how to compute. So Schubert calculus was kind of had been developed to some extent by then, and this was an integral that for which the tools were available to compute. And this is some sort of generalized Catalan number. So when r is 1, this is really an honest Catalan number, and when r is bigger than 1, you get something that sort of looks similar. Okay. All right. So now I want to go to kind of a very different setting. So this is 100 years later, so around starting in the 1990s. So from 1990s. And okay, so let me state a theorem, and I'll do the attributions later. So in fact, in the 90s, so this is when Gromov-Witten theory kind of took off, and in the formulation that I've given, in fact, the calculation of the virtual degree of tau, or of tau bar, was one of the first successful calculations in Gromov-Witten theory. And what was found is that the virtual degree of tau has the simplest possible formula. It's r plus 1 to the g. Okay, so the virtual number of curves of fixed domain passing through a maximal number of points in PR is r plus 1 to the g independently of the degree of the map. So to my knowledge, the first time this formula had appeared in the mathematics literature is in a paper of Bertram, Daskalopoulos, and Wentworth, which is around 96. So one of the amazing things about this paper is that, okay, I think 96 is the publication date, but when the paper was actually written, this was before the sort of this kind of Baron-Fentecchi machinery was developed. So before we had kind of a systematic language of virtual classes. So these authors had a way of arriving this number, which they understood to be a virtual count, kind of before we had virtual invariants in the modern language. Okay. And they actually did much more than this, but maybe I'll save that. So Siebert and Tian reproved this, and also something much more general, I think, a little bit later. There, even the language of virtual classes was, again, not quite fully developed. There's work of Mariano Noprea in 2007. So by then we had kind of quote schemes and space of stable maps and virtual classes. And so their calculation is what you might understand to be kind of the first modern calculation of this and something much more general in the language of virtual fundamental classes. And maybe I should also add plus Pandura Pandey. So Mariano Noprea did something on kind of some sort of virtual calculation of the quote scheme, and then it was later explained in a paper with Pandura Pandey that this is actually equivalent to the formulation I gave. And then most recently, so Buch and Pandura Pandey gave kind of a new kind of viewpoint on this, where you can replace PR with any target. In fact, this is sort of a new viewpoint, but also not quite a new viewpoint, because it's using the language of which had been available for 20 years. But what they explained is that actually they explain what seems to be the most direct calculation of this invariant. So what they explain is that you can reduce the calculation of the calculation to some sort of calculation in the quantum cohomology of PR. Okay, and the quantum cohomology of PR at this point is some sort of easy object, right? So this is at this point, I now view this as actually a rather straightforward calculation. So I'm claiming this calculation is kind of easy, but in fact, all of these authors did much more than this. So let me just mention this. So in particular, the papers of Siebert Tian and Mariano Noprea, and then to a partial extent, the previous paper of Bertram Duskalopoulos Wentworth. So they prove actually what's called the Waffen trilogator formula. Which comes to us from string theory, and this determines so all virtual counts, so virtual counts of maps from a fixed curve to any Grassmannian with kind of arbitrary Schubert incidence conditions. Okay, so this is a generalization in two directions. You can replace the projective space with the Grassmannian, and you can replace these point conditions with any Schubert conditions. You might call this, as Bertram did, quantum Schubert calculus. Okay, but on the other hand, again, this is a virtual degree, and none of this actually determines the answer to theorem A. Right, so theorem A is sort of not seen by any of these virtual calculations. In fact, theorem A is much harder than the virtual calculation. All right, so now let me fast forward to 2020. So in 2020, Genia Tevelev, so he gave a calculation. So to my knowledge, Tevelev was the first person to really ask, like, okay, we have like all these virtual calculations are in the literature, but what is the actual degree of this morphism? So what he found is that so for P1, if you take the genus to be arbitrary, the degree to be G+1, and the number of Marx points to be G+3. So this is, of course, this is counting maps of a genus G curve to P1 of degree G+1 with G+3 conditions. Then the degree of tau is again 2 to the G. Okay. So this doesn't go through any Gromov-Witten theory or anything. So this agrees, notice, with the virtual degree. So when r is 1, you just get 2 to the g. But he had some sort of very different calculation that he was interested in for other reasons. Okay, and then so the genesis of this was that Tevelev was discussing this work in fact, an online seminar in Zurich. And so a few months later, Alessio Cella, Rahul Pandey, and Johannes Schmidt, they gave a calculation of all of these invariants for maps to P1. So the theorem is that when r equals 1, and d and g arbitrary, or d and n, I should say, arbitrary, what they found is that the degree of tau, well, okay, so I'm not going to write their complete formula, but it's 2 to the g, and then kind of minus something else. Okay, so this something else is not, I mean, it's like some kind of sum of binomial coefficients. But let me just say something. So this something else is 0, so vanishes when d is at least g plus 1. So what you could say is that, well, when d is at least g plus 1, when d is large compared to the genus of the curve, then you just get the Gromov-Witten answer. You get the number r plus 1 to the g, right? So you get this answer. But when d drops below that threshold, when d is small, you really get something different, right? So that virtual invariant stops being enumerative, right? And so what's happening there is that the virtual, like this picture that I drew of with this constant map out of C, will start playing a role when d is small. And so what they do is they have some other methods that kind of avoid all of those contributions and give you a different number, right? So they work on this is via Hurwitz spaces. So this is via intersection theory and moduli spaces of branch covers of P1. Okay. So this was 21, and then this was around March 21, and then a couple months later, Gabi Farkas and I had a different way to do this. So maybe I'll state two theorems here. So when r equals 1, so the degree of tau is well. So we arrived at the formula from theorem A, which I stated at the beginning. So that's some Schubert calculus formula, and so the methods that go into that are the methods I'll explain hopefully by the end of the talk. Okay, so this is still r equals 1. And moreover, when r is arbitrary, and I need to add an important condition here, d is at least rg plus r. So when d is again large, the degree of tau is equal to the virtual degree. So the Gromov-Witten invariant is enumerative, and it's equal to r plus 1 to the g once more. Okay. So what we're seeing here is that when d is large, so in theorem B here, and also in the theorem of Tevelev-Schmidt, what we're seeing here is that when d is large, the Gromov-Witten answer is correct. And this is actually a somewhat general phenomenon. But when d is small, it's just not. It's just you just do not get r plus 1 to g. In fact, we already saw this in the Castelnuovo answer. So in the Castelnuovo answer, that's when d is kind of as small as possible, and you get some kind of generalized Catalan number, which is kind of very far from the number r plus 1 to the g. So what you can think is that all these theorems are saying, well, there's kind of two extremes we understand. There's sort of the lowest degree possible, which is the Castelnuovo answer, and then there's sort of large degrees where the Gromov-Witten answer is correct. And then in between, you need to interpolate between these two answers, and that's what's kind of missing from this picture. And this is what theorem A gives you. So theorem A, this kind of interpolates between sort of the Castelnuovo. So maybe if you sort of take a number line, I guess this is sort of d, but this is sort of d very small, so d as small as possible. And then, so above some range, there's some kind of Gromov-Witten answer. And then over here, this is where theorem A kind of gives you something new, sort of new results. Okay. Okay, so are there questions about these previous results? Okay, so in the rest of the talk, I want to kind of explain where some of the pieces of this theorem come from. So so in this theorem, I have there are kind of three parts, and I'll explain two of them. So I'll explain where this class comes from. This is actually the class appearing in Casanova's calculation. And I'll explain where this class comes from. This one's a little more complicated. And I will not explain where this kind of subscript comes from, and I'll sort of sweep that under the rug. Okay. So ideas from proof. Okay, so the first step is some degeneration to genus 0. So so to start with, I've again fixed a general curve in moduli, which is just smooth. And I mean, the kind of convenient thing about working with a fixed curve is I can replace that fixed curve with a singular curve. So for this discussion, I'm going to replace it with the cuspidal curve because it's just the easiest to say. But secretly, this is not what I'm actually doing. Okay, so I'm gonna replace C with like a G cuspidal curve. So it has G cusps, and when I normalize, I get a rational curve. It still has n mark points on it. And okay, well, if I have a curve, if I have a map out of my smooth curve that satisfies n incidence conditions, I want that to degenerate to a map now out of this cuspidal curve, but after normalization, it'll be a map out of a genus 0 curve, so from P1 to PR. Still satisfying these incidence conditions. But this is a map out of a cuspidal curve now, and there'll be an additional condition in the limit, which is that f is ramified at the points, or I guess the pre-image is under normalization at the points Q1 through QJ. Sorry, QG. Okay. And by ramified here, I mean that like the tangent vector at P1 goes to 0 under F. Okay, so that's like R conditions. Okay, and another way to say that is that, well, if you take the linear series of sections of F, right? So F is determined by like R plus 1 sections of the line bundle OD. And if I take so there'll be a hyperplane's worth of sections that vanish at the point Q for any at the point say Q1, and the condition is that actually all R of those sections vanish to order 2. Right. So let me say that. So in other words, so the hyperplane of sections defining F that vanish at Qj actually vanishes to order 2. And so this kind of geometric condition is the key one. So this is equivalent to equivalent to the Schubert condition of class sigma 1 to the R on this Grassmannian of this Grassmannian of R plus 1 planes inside the space of sections of OD. So this is grid D. Right, and this is where the first part of this formula comes from. So this gives you the class sigma R and the G after varying over all G of the points QI. Okay. So this is the general idea. I mean, so this takes quite a bit of work to actually make precise. But let me say what kind of the needed ingredients here. So needed ingredients. So one is this Eisenbud-Heron's theory of limit linear series. So in the theory of limit linear series, you don't have cuspidal curves, but you have stable nodal curves. And so actually these cuffs are secretly kind of elliptic tails that I've contracted. But there's a slight issue here. So now in the year 2023, we understand Castanova's calculation in this language of linear series. But in this setting, we're not just concerned with linear series. So a linear series is a map to PR, like up to the PGL2 action, PGL R+1 action. But here I don't want to consider things up to the PGL R+1 action because I really have like incidence conditions at points which for which if you apply the PGL R+1 action, like you'll just get different incidence conditions. So and the problem is somehow that these, like, I'm interested in these R+1 sections, and the thing that I've not mentioned is, well, you can start with the map from C to PR, and the thing you're really worried about from the example that I gave earlier, where these virtual degrees are not equal to the geometric degrees, is that these sections can somehow degenerate and kind of like, I guess the fundamental problem is like, well, how are you going to avoid this picture? So you could end up in situations where these maps still degenerate to kind of bad things that look like this in this example. So in this example, I've drawn kind of a Gromov-Witten picture, but you can also interpret this example as saying, well, what if my map from C to PR degenerates to some kind of constant map from P1 to PR, where I introduce a bunch of base points, right? And you know, I stated this generation in terms of some kind of Grossmanian, and well, you might complain. In fact, you should complain that, well, what if these maps, what if these sections F are no longer linearly independent in the limit, right? So, you know, I'm thinking of some kind of R+1 dimensional space of sections defining this map from P1 to PR, but my map could degenerate, right? Like these sections could become dependent in the limit. And so the beautiful thing that kind of fixes all these issues simultaneously is what's called the space of complete collineations. So the space of and this is what's actually kind of the engine that's allowing you to avoid all these Gromov-Witten contributions. So avoids kind of contributions. Maybe I won't say Gromov-Witten, but I'll say contributions from maybe maps with base points by blowing up loci of degenerate maps. So here by degenerate maps, I actually don't mean maps with base points, but I mean maps with image contained in a hyperplane. Okay. So it turns out, so this is maybe a technical point, but so it turns out that the only bad maps you have to avoid by Brillen-Noether theory are degenerate ones. Because so Brillen-Noether theory tells you that as soon as you have a map that kind of that's defined by a linear series of rank R, so it's defined by R+1 linearly independent sections, then those maps cannot give you any bad contributions. Those maps will move in families of the expected dimension. So the worst thing you have to avoid is kind of like constant maps, right? Those are maps where you have like R+1 sections that are all scalar multiples of each other. So these are clearly very bad, and all these sort of bad loci have to be blown up. And this is what this space of complete collineations is gonna do for you. Okay. So in the end, maybe I'll just state what you get at the end of this degeneration. So you're reduced to the following problem. So I can think about the space of maps now out of a rational curve with f of pi equals xi. And this admits a rational map to the Grossmanian of R+1 planes in forms of degree d, right? So the map is just you take the underlying linear series if that linear series is non-degenerate. And the question is, well, what is the class of the image, or I guess maybe I should say the closure of the image, which I can call, maybe I'll call it like Y, R, N, D, inside the Grassmannian. Okay. And of course, the issue here again is I have a rational map. So what the space of complete collineation is going to do for you. So I haven't defined this space, and I won't. But this will be kind of the correct resolution of this map. So space of complete collineations. And this is sort of the correct place to work. And this will be kind of an honest algebraic map. Okay. But even if you just take the rational map, I mean, this is kind of a well-formed question. And so this reduces the problem to some genus zero calculation. Okay. All right, so now I want to say something about this genus zero problem. And there are actually two ways out. So there's one quick way to finish. So the first thing you can do is you can reduce, and I'm not going to explain this step at all. You can essentially reduce to the case when d is n minus 1. Okay, and I'm not really going to explain why that's kind of what's special about that case. But what happens in that case is that, well, when d is n minus 1, this space, actually for reasons that are not super hard, this turns out to be agrees with or I should say is a generic torus orbit closure. Well, period. So what do I mean by this? Well, okay, so this Grassmannian, so D is n minus 1 here. So this is like the Grassmannian of R plus 1 planes in Cn. And then on this Cn, there's kind of a C star to the n that acts. And that C star and that torus action induces a torus action on this Grassmannian. So you can take a generic point of the Grassmannian, you could hit it with the torus and then take the torus orbit closure. And that's a subvariety of dimension n minus 1. And these torus orbit closures are very well studied. So they're super important, for instance, in matrix theory. And in particular, the classes have been understood by various people. So these classes are understood. Why I did red. So for instance, they were computed in the 80s by Kliachko. For kind of more general flag varieties, there's so there's a different formula by Anderson and Tomashko on the full flag variety, and this actually specializes, but Birgit and Fink gave a different calculation, which is kind of a special case of the Anderson-Tomashko formula. But let me just state the Birgit-Fink formula. This is around 05, and this is the 80s, and this is I think 2012. And so they get the answer which we've seen already. And I still haven't really explained where these Schubert cycles are coming from, but so they prove this. Okay, so I just want to mention, I mean, if you want kind of a quick proof, this is a way to finish. Now, what I'd like to explain in the last 10 minutes is actually a new way to arrive at well, actually, not just the Birgit-Fink formula, but also the Anderson-Tomashko formula, which I won't state. So I want to kind of mention a new calculation of this class in the context of the problem that I started with, and the reason I want to mention this kind of new viewpoint is that all of the previous calculations of orbit closures, I was not able to push to prove theorem B. So I mean, at this point, I know at least 5 or 6 ways to compute the class of the orbit closure in the Grassmannian, and I don't know how to generalize any of them to the kind of the more general setting where I count curves with incidence conditions of arbitrary dimension. But what I'd like to explain will actually generalize to theorem B, and will generalize and we'll kind of go further, assuming one can get over certain combinatorial hurdles. Okay. So what I'd like to explain now is so the class of y, r, and d, and then this is by degeneration of the points xi and pr. So remember, this class y, r, and d is this class on the Grossmanian that I get from maps out of a rational curve with n incidence conditions. Okay, so in this particular recovers orbit closure formulas. Okay. All right, so I'm going to go back to the geometric situation. So to recall, so I'm studying maps from P1 to PR, where points pi are supposed to map to points xi. And the idea, okay, so now I'm going to do yet another degeneration. So now my curve has degenerated to genus 0, but now I'm going to start degenerating my points. And more precisely, I'm going to move the points x1, x2, and so on, one by one onto a hyperplane in PR. And then I'm going to study the degeneration of F. Okay. So the picture is as follows. So I'm going to start. So maybe you imagine, I don't know how to do it this way. So maybe here's PR. And I'm going to fix some hyperplane. It's going to be my H. So H is, of course, isomorphic to PR minus 1. And so I want to imagine that initially I have, let's say, like alpha points. So x1 up to x alpha that I've already moved onto H. And then I have a bunch of points that are not on H yet. So sorry, I don't know why I'm shrinking. Sorry about that. So I have a bunch of points that are not yet on H. And then, okay, so I've had a gap here. So then I'm going to take x alpha plus 1. And then I'm going to imagine moving my point x alpha plus 1 closer and closer to H, and then until it lands on H. Okay, so then on the general fiber of this degeneration, I have some curve, right? And it passes through all n of these points. And then I'm gonna, as I said, I'm gonna take this point and kind of move it onto H. So now, okay, there are two things that can happen. So one thing that can happen is I can just move my point x alpha plus 1 onto H, and then everything sort of stays the same. I still have this purple curve, and it's still kind of passing through all n minus all n points, and in particular, if it's passing through a bunch of points that are not on H, that's telling you that this curve is kind of intersecting H transversely. Okay, so so one thing that can happen is I could just redraw this picture, but put x alpha plus 1 on H. But the other thing that can happen is like, well, the more points you put on H, the more the curve just wants to live only on H, right? So the other thing that could happen is that this could degenerate to something that looks like this, where, okay, so my hyperplane again, and now I have alpha plus 1 points on H, so x alpha plus 1. Plus 2 to xn. And now my curve could just kind of collapse into H. And you might ask, well, wait a minute. So why is this suddenly allowed to happen if I have a bunch of points that are like not on my curve anymore? Well, so what's going to happen here is that P alpha plus 2 up to Pn become base points. So this is now a map from F from C to like H, which lives inside PR. So these PI become base points of F. So they don't map to the xi, but they kind of satisfy the linear conditions that kind of make it look like they're mapping to xi. But then the question is, okay, well, like, why is it suddenly allowed to do this? Well, the reason is that if you have curves mapping, if you have curves moving around on a hyperplane instead of in PR, if I allow my curve to stay in the hyperplane, then it's only so. If you have a curve in PR, then it's R conditions for PI to map to xi, right? Because there's like an R-dimensional family of points PI can map to. If you stick to curves to H, it's only R-1 conditions to map to a point on H, right? So you kind of gain, you kind of gain a degree of freedom if you allow your curve only to move around H, and you can kind of bank that degree of freedom and allow your curve to kind of be a base point for all these other points that are not on H. Okay. Now, there's something that's still missing. So if you actually do the dimension count here, what you find is that actually in this degenerate picture I've drawn, there are actually a strictly smaller number of, now you actually have strictly more degrees of freedom in the picture downstairs. So actually in the picture downstairs, there's still too many things. There's some additional conditions that are missing. And what's actually missing here? Well, if I go back to the general fiber, there's a condition here, which is very special. Namely that, well, if I have a bunch of points on H, then the corresponding points P1 through P alpha have to kind of admit a secant. So what this is saying is that, so here I have kind of a non-degenerate map from C to PR. And furthermore, there exists a section in the underlying linear series that vanishes along the divisor. So you might think of this section as a secant. The divisor P1 up to P alpha, right? Because this is a very special condition, right? In this picture on the general fiber, I'm asserting the existence of a section that vanishes at like a particular divisor of large degree, right? And this will not happen if you just have a random linear series on C. And on the other hand, if you take the limit of this map to PR, that section becomes invisible, right? The section becomes zero. Once your map just stays in H, that section has been sent to zero, right? So I've lost the data of that special section. On the other hand, if you remember not just the map from C to PR, but the limit of the span of the sections, right? So up here I have R+1 linearly independent sections. On the special fiber, one of those sections becomes zero, but I can still remember the limit of the kind of R+1 dimensional subspace of H naught of OD. So in the limit of the linear series underlying F, so maybe I should say the limit, still contains, maybe I'll limit, still contains a secant vanishing, so really a non-zero secant along P1 plus P alpha. Okay, and that secant would have been invisible if you only remembered the map. But if you remember this additional section, which is sort of no longer visible just in this geometric picture, then you actually get a non-trivial condition. Okay, so you might call this kind of a base point condition. You might call this a sequency condition. And then, okay, so I realize I'm out of time, but let me just say what happens in the end. I'll stop. So now when I get to this point, now I have a map in H, and then now I repeat. So now I move x1 through x alpha plus 1 into a codimension 2 subspace, and then I iterate. And what will happen in the end, so I get two things. I'll get a nested sequence of base point conditions, and I'll get a nested sequence of sequencing conditions. And these will turn into precisely these Schubert cycles, sigma lambda and sigma lambda bar. Okay, I'll stop there.